Hello, welcome back. This is lesson 3 of our Waves and Oscillation unit. We are going to cover classification of waves, wave terminology, calculating the speed of a wave, and electromagnetic waves. So let's start with classifying waves. One way to classify waves is transverse or longitudinal. This video is going to cover what transverse and longitudinal waves are, examples, and properties of all waves that are listed on this chart. First of all, some vocabulary. Some of this is going to be review. Wavelength is the distance along the medium between two successive particles that have the same displacement and the same phase of motion. The symbol for wavelength is lambda. This is the Greek letter lambda, and this is the symbol we use for wavelength. Obviously, the SI unit, since it is length, is the meter. Time period T, the time it takes for one complete cycle of the wave. Since it's time, SI unit is the second. Displacement X is how far the particle has traveled from its mean or equilibrium position. Wave speed V, measured in meters per second, it's the speed with which energy is carried in the medium by the wave. And intensity, capital I, is defined as power per unit area that is received by an observer. Intensity is proportional to the square of the amplitude. All of these terms are content of this video. Intensity will be discussed later. So, first of all, let's understand what is a pulse and what is a continuous wave. A single shake. So that is a pulse. Same simulation we can use for showing continuous waves. Continuous traveling waves look like this. The distinction between transverse and longitudinal waves depends on the direction of motion of the particles. Watch my hand and how I move the slinky. So, compare this to that. Again, observe the motion of my hand creating the wave. So take a moment to think about the difference between the two examples you just saw. In the first one, my hand was moving vertically. In the second one, my hand was moving horizontally. In both cases, the wave was moving across the medium horizontally. So let's start with transverse waves first. What do you see? You should be seeing a wave going across the medium in that direction. Let's watch again. That is the direction of energy propagation. Well, a wave is a transfer of energy. So in any wave, you should look for which way the energy is being transferred. In this case, it's being transferred to the right. Now observe what each particle of the medium is doing. It's moving vertically. It's moving up and down, where the wave is moving to the right. This is what a transverse wave is. Now, I have a suggestion for you if you want to make transverse waves at home. You probably don't have a slinky, but you might find a long rope and try this. Set your rope on the floor and mark a point or two somewhere on the rope. And then move your hand sideways and observe the wave travel away from you. As you do that, watch the motion of this point you marked on the rope. Let's watch. It's obviously not perfect, but this is something you can do at home to see the motion of each particle or a point of the medium when you create a transverse wave. Now, another way to create a transverse wave is this. Do you see the wave moving to the left? And do you see each soldier is moving up and down. They're squatting really, but one at a time. Let's see again. So here we go, transverse waves. So a transverse wave, wavelength is the distance between two consecutive peaks, which are called crests. Wavelength can also be measured from two consecutive minimums, which are called troughs. Wavelength can also be measured from one equilibrium point to the next equilibrium point, which the wave starts repeating itself. So that distance is not one wavelength, it's half a wavelength. The particles move perpendicularly to the propagation of the wave. In this case, the wave can be moving to the right, and each particle is moving vertically up and down, just like the soldiers we just saw. In that case, each particle actually is said to be oscillating. So this is the equilibrium position of the motion of the particles. That would be one amplitude, and that would be another amplitude as shown here. Wavelength measured from one crest to the next, and amplitude measured from equilibrium point to a trough or equilibrium point to the crest. Obviously, this is not a perfect waveform because I was moving the slinky by my hand, and also there is damping. So you expect to have some energy loss due to the friction with the floor. Here's another image to show transverse waves. You can see that the oscillation of particles are vertical, where the waves is seen to be moving towards the right. So here's the formal definition. A transverse wave is when the displacement of particles of the medium is at right angles to the direction of the wave. For example, a wave on a rope or light. But in the light case, the electric field vector is oscillating, not the particles of the medium. We'll get back to this at the end of this video. One example of graphs we draw to represent waves is displacement distance graphs. Now this may sound odd because in motion we never draw distance versus distance because it's meter versus meter. What does that even mean? Well, the vertical displacement axis refers to the displacement of the particle in a medium. So that's the oscillation of a particle. You can see this as a snapshot at any instant of a transverse wave. And the wave is moving to the right, but this is not a time scale graph. So we plot displacement of a particle in the medium versus distance measured along the wave, which is why distance between two crests will give us the wavelength. And the reading of that number right there would be the amplitude. We can also draw displacement time graphs for transverse waves. In that case, the vertical axis is identical to the graph I showed you, but the horizontal axis is now time, which means the measurement between two neighboring crests will now show the time from one crest to another, which is defined as the time period. So that kind of graph will give us wavelength information, and this kind of graph will give us period information. Both graphs will give us the amplitude reading from the y-axis. Here's an example of what this might look like. A close-up of the motion of a spring can represent the motion of a particle that is oscillating in a wave. As it does that, when it's at the maximum displacement, you can see that in here. As it passes from the equilibrium position, it's somewhere here. When it reaches its minimum position, that is right there, and it keeps going up and down and up again. Let's watch this again with the understanding of the link between this oscillation and what we see at the bottom. As I explained before, the vertical axis is the displacement of a particle in the medium. Now, if you're creating a wave by moving the string up and down and the wave moving forward, as I said, the particles are moving vertically in oscillation. But how can we tell instantaneously which direction each particle is moving during an instant? So I'll go back to this simulation, but now I'm going to label some points. That would be particle A, particle B, particle C. This is the equilibrium position. And we are given that the direction of the wave is towards the right. So, with only this information, can you tell me which direction should particle A be moving? Is it on its way down or is it on its way up? Then answer the same question for particle B and answer the same question for particle C. Pause the video, take a moment to think about this. Since the motion of the wave is towards the right, the instant right after this moment, the wave will have shifted to the right, which means particle A has not reached its maximum yet. The particle before that is at its maximum, so it must be coming down. It has gone up, now it's coming down. But since this is up, it's going to transfer the energy to that particle, and that particle will transfer its energy to A. So it's still on its way up. So particle A must be moving upward in this instant. Let's look at particle B. If you shift this yellow curve slightly to the right, you are going to see the next instant particle B is going to be in that location because that's what the particle right before that is doing. The energy of the particle right before that will be transferred to the particle you're looking at. There are two ways to answer this question. One way is to shift the curve to the right, which is in the direction of the motion of the wave, and see where the particle lands. Or the second way is to look what the previous particle is doing, and that's where the particle is going to be in the next instant, so it must be moving in that direction. Likewise, particle C is also moving up. Can you find any particles that are moving downward in this example? This particle must be on its way down because look at the previous particle, it's at a lower position, and that's where this particle is going to be in the next instant. So this particle must be on its way down. Now let's talk about longitudinal waves. Similar simulation which shows the individual oscillation of particles along a longitudinal wave. So I have marked 2 points on this simulation. Look at that particle. I'm going to use the midpoint of the particle to represent the position of the particle. At this moment, the particle is at its farthest right amplitude. This is the location of its farthest left amplitude. Now, I'll play the simulation and I'd like you to watch and see that this particle is oscillating between these two lines. This means the equilibrium point is in the midpoint of these two lines, so half the distance between two lines is the amplitude of this particle. And that is how we determine the amplitude of particles on longitudinal waves. Let's see how longitudinal waves are labeled. Remember, for transverse waves we had crests and troughs. Well, for longitudinal waves we have compressions and we have rarefactions, in other words expansions. So you're going to see where a slinky is more compressed and regions where it has expanded. Another region where it's compressed, another region where it's expanded, just like crests or troughs of transverse waves. Now, in this case, the direction of the wave is to the right, But we have seen in previous videos and the simulation that the direction of vibration of individual particles is actually in a parallel direction to the propagation of the wave. Using the screenshot from my initial video showing you a longitudinal wave, this is the middle of one compression, and that is where I just start the next compression. So the distance between those would be measured as the wavelength. And like I said before, each particle is doing that motion. So half of this would be one amplitude. And defining longitudinal waves. They are when the oscillation of the particles of the medium is in parallel to the direction of the wave. Example of longitudinal waves is sound. Okay, before we move on, let's think about what frequency means for longitudinal waves. Now, this is a recorded sound. It might be a little disturbing, but please bear with me and observe what frequency means for sound. Okay, I recap. Transverse waves, particles oscillating perpendicularly to the direction of motion of the wave, wavelength measured between two neighboring crests or troughs. Longitudinal wave, oscillation of particle in a parallel direction to the propagation of the wave, wavelength measured from the middle of one compression to the middle of the next compression. How do displacement distance graphs look like for longitudinal waves? Well, actually, they look exactly the same. So what does it mean to have a picture like this for a longitudinal wave? Now, if I'm drawing a displacement distance graphs for a longitudinal wave, it might look exactly the same, but we need to change our perspective a little bit. You will remember this particle from the simulation before. This particle is moving between these two maximum points. So if you change your perspective and tilt this 90 degrees, place that on the vertical axis, you will see that we have exactly the same graph. Here is what I mean. So that's the tilted version. Imagine the x-axis, the horizontal axis you see in the graph above, is at that point. So as the particle moves up and down in this case, you will have exactly the same graph. Okay. To explain displacement distance graphs in longitudinal waves a little bit more, I've added more labels to the graph. So above the origin is where the particle is to the right of its equilibrium position. Below the origin is where the particle is to the left of its equilibrium position. Like we saw in the simulation on the previous slide, the particle is oscillating parallel to the wave, but we have rotated its oscillation by 90 degrees counterclockwise to locate it on the vertical axis on this graph. Here's another note I'd like to add before I move on to the displacement time graphs for longitudinal waves. On a graph like this for longitudinal waves, that would be the center of a compression, and that point would be the center of an expansion. Here is why. Look at this picture. That would be the center of a compression, right? If the wave is moving to the right, to be in the center of a compression, the particles on its left must have traveled to the right, and the particles on its right must have traveled to the left, so that this point has been squeezed by its neighbors. It's the opposite for the center of an expansion. If a particle is the center of an expansion, the particles on its left have moved more left. The particles on its right have moved more right, basically away from this particle. How we see that on the graph is, look at the left of the particle. There's left displacement on its left. On the right of the particle, there is right displacement. So this must be the center of an expansion. Look at that point. This point is the center of a compression because the particle on its left has right displacement. The particle on its right has left displacement. Okay, moving on to displacement time graphs for longitudinal waves. Again, the vertical axis is the displacement of the particle of the medium. So this would be the amplitude of a particle. And since the horizontal axis is labeled as time, the measurement between two neighboring peaks would give us the time period. Okay, how do we calculate the speed of a wave? Let's see examples first. There are 6 strings on this simulation, and they all have different thicknesses, and they are under different tension. So the wave travels at different speeds in each. When we learn about refraction in our future lessons, we are going to learn that the speed of a wave depends on the medium it is on. So the properties of each string is what determines how fast the speed is traveling on each. But how do we calculate the speed of a wave? So we know the speed is given as distance over time. Well, speed of a wave can be calculated by distance traveled by a wave in one period of time. The name we give to distance traveled by a wave in one period of time is wavelength, divided by time period, which looks like this. V equals lambda divided by t. Obviously, this would be meters per second. I can also write frequency as 1 over t, as given in the data booklet. Replace 1 over t by frequency, we get V equals F times lambda. This is called the wave equation. In the data booklet, this is given under subtopic 4.2 as C equals F times lambda. C means the speed of the wave in this context. A quick demonstration about the relationship between frequency and wavelength before we move on. I am able to change the frequency in this simulation, and we said before that the speed of a wave changes only if the medium changes, which in this case will be constant because I'm not changing anything about the string. All I'm changing is the frequency of oscillation of the source. So we are measuring about 4 centimeters for the wavelength from crest to crest when frequency is 1 hertz. Let's see what that looks like. Let's increase the frequency to 2 hertz. What do you expect? As you can see, the wavelength has now changed to about 2 centimeters. So, as long as the speed of a wave is constant, high frequency means low wavelength, and vice versa. Okay, our next discussion is electromagnetic waves. Now, this is the electromagnetic spectrum. What you need to know about the electromagnetic spectrum: the order, radio to gamma rays, from low frequency to high frequency. You have to be able to rank the sections of the electromagnetic spectrum. Electromagnetic waves can travel through vacuum. They don't need a medium to deliver the energy, so they don't need particles to be oscillating to travel. This is how light can travel in space. All electromagnetic waves are transverse waves, where the electric field vector and the magnetic field vectors oscillate perpendicular to each other. Here's what that looks like. So the yellow arrows represent the electric field oscillation, and the green arrows represent the magnetic field vector oscillation. You might remember from topic 5, a moving charge creates a magnetic field in the direction perpendicular to the motion of the particle. Linking that to this unit, when a charge oscillates, its electric field oscillates with it. An oscillation means it's constantly accelerating. That means its magnitude is constantly changing, and that means in a perpendicular direction, the magnetic field vector is also changing. So what you need to understand is that all waves travel at the speed of light in vacuum. This value is given in the data booklet. The types of electromagnetic waves in order of increasing frequency or decreasing wavelength is what you need to know about the electromagnetic waves. The range of wavelengths of the visible spectrum, you can look that up. And suggest which section of the electromagnetic spectrum given the wavelength or frequency. Now, I want to show you what frequency or wavelength means in terms of electromagnetic wave. Remember, wavelength means pitch for sound. For light, it means color. You should see that all these waves are traveling at the same speed, but moving from radio to ultraviolet, the wavelength is decreasing. So that's it for this lesson. The follow-up activity, solution of which you will find on my next video, is in your workbook from page 169 to 172. All of it applies to HL students, and only the given ones on this slide applies to standard level students. Thank you.